Hello everyone, today I'm very pleased to join IEEE MLSP to present our work, C3-SL, Circular Convolution-Based Batchwise Compression for Communication-Efficient Speed Learning. This work is done by Cheng-Yen Hsieh, Yu-Chuan, and Professor An-Yeu at National Taiwan University. I'm the presenter, Cheng-Yen Hsieh. This is the outline of our presentation. First, I will introduce speed learning and feature compression. And then I will present a new compression paradigm, batchwise compression. And then I will show the overall framework of C3-SL. The experiment results will verify the effectiveness of C3-SL. And then I will conclude. The training of speed learning consists of two main parts. In the splitting steps, we divide the DNN into two separate parts, where we deploy the former part of the neural network in an edge device, and the later part of the neural network will be deployed in the cloud server. The training steps begins from feeding input images into the former part of the DNN and obtain intermediate features. The intermediate features will be transmitted over to the cloud server and fed into the later part to complete the forward propagation. In the backpropagation process, the cloud server computes the gradients with the transmitted labels and propagates the gradients backward. To further improve the efficiency of speed learning, many previous works utilize dimension-wise compression that transforms high-dimensional features into a low-dimensional space. Specifically, dimension-wise compression utilizes extra NN models such as encoder and decoder to embed features into a low-dimensional space. Although many previous works have been devoted to compress features in dimensional space, no work investigates the possibility of compressing a batch of features into one single feature before transmission. Thus, in this paper, we explore the potential of a new compression paradigm, batchwise compression. In this paper, we first propose a circular convolution-based batchwise compression for speed learning, called C3-SL, to efficiently reduce communication cost. The proposed C3-SL consists of two main modules: the encoder, where we utilize circular convolution and superposition to compress a group of features into one single feature, and the decoder, where we utilize circular correlation, the inverse operation of circular convolution, to decode each compressed feature back into a group of features. Below, we will discuss more details about the two modules. To merge each feature into one single feature, naively, we may directly merge all of the features into one single feature with superposition. However, if the feature is close to each other in the original space, the merging process will produce information loss, and it will be difficult to decode the original features with the compressed features. Thus, in our framework, we use circular convolution operations. We first generate two random keys, K1 and K2, with normal distribution, and bind the feature vector with the generated keys. The binded features will be quasi-orthogonal to each other. As a result, it will be easier for the merged feature to preserve the information of the original feature. Accordingly, it will be easier to decode the original features. To be more specific, for each batch of features, where B denotes the batch size, we divide them into B over R groups of features. For each group, we use circular convolution and our generated keys to bind each feature. Then, we utilize superposition to merge each binded features into one single feature. We use S to denote the compressed feature for each group. It's worth noting that the operation is continuous. So, during the backpropagation, the gradients could be calculated. However, C3-SL does not compute the gradients for keys or update the weights of keys. This reduces the computation burden compared to dimension-wise compression techniques. The compressed feature for each group will be transmitted to the cloud server. In the decoder, we use circular correlation, which is the inverse operation of circular convolution. The decoder uses circular correlation to retrieve the original features back from the compressed features. The retrieved features will be fed into the later part of the neural network and complete the forward propagation to compute the training loss. Although this process is noisy, the performance drop is negligible and will be demonstrated later. To verify the effectiveness, we compare the proposed C3-SL to bottleneck double plus, a SOTA that utilizes dimension-wise compression techniques. We train VGG 16 on Cipher 10 and ResNet 50 on Cipher 100. As you can see, C3-SL achieves negligible accuracy drop compared to vanilla SL, whose features are not compressed at all. We also obtain competitive accuracy with bottleneck. Besides, C3-SL greatly reduces the number of parameters, that is, the memory overhead and the computation overhead. This shows that under the speed learning scenario with limited memory and computation resource, C3-SL is more suitable to compress the intermediate features. To conclude, in this work, we propose C3-SL, circular convolution-based batchwise compression for communication-efficient speed learning. We explore the potential of a new compression paradigm, batchwise compression, by compressing a group of features into one single feature. To avoid information loss, we explore the quasi-orthogonality of features in high-dimensional space with circular convolution and circular correlation. With the designed experiments, the memory-efficient and computation-efficient property of C3-SL are properly verified. For the future work, we will keep exploring the potential of combining dimension-wise and batch-wise compression techniques. If you are interested in this work, feel free to visit our official GitHub repository, where you can also find contact information of the author. I'm today's presenter, Cheng-Yen Hsieh. Thank you for listening.